Okay, so as I said in the last one, right, this is what I planned to do before, right? So yeah, it's really interesting. It just occurred to me one day. So and then I thought that it was unique, but apparently it's not. Yeah, it's been thought about since like 1996 or 7 or something like that. Yeah. So yeah, anyways, so so it's like the Euler-Tochian function of two consecutive numbers are equal. So what can those consecutive numbers be? That's what occurred to me one day. So this is like, I think this is like a research topic because like no one knows, but I guess we can try, right? Why not? Anyways, so yeah, today what I'm going to do is I'm going to suppose that either one of these is prime. Now, what I'm going to do is I'm going to suppose that n is prime, right? Set n equal to p prime. Right, this is just something I'm letting it equal to just so like notation is clear. Anyway, so just so you know, the phi of any prime is equal to the prime number minus 1, because it's like, okay, so you can think of it as basically every number is co-prime to it, right? Yeah. So anyways, that's a very well-known fact. So I'm just going to use that directly. So what we're going to get is so p minus 1 is equal to, okay, so this is going to be phi of n plus 1. Now let's study this n plus 1 object, right? So firstly, okay, so there are two cases. P can either be odd or even. It can only be even if it's 2. So yeah, so the only case when it's even is when it's 2. So now that's like C1 P equals 2. That implies that phi of n plus 1 equals 1, but like phi of 3 is clearly not equal to, wait, no, that's not how you write. It's clearly not equal to 1, so that's like a contradiction. So that can't be a case. Anyways, so our case 2 would be that p is odd, right? So if it's odd, then n plus 1 even. So that just means that this is a really haywire way of saying that 2 divides n plus 1, right? Now we don't know yet if 3 divides it, but 2 does divide it without any problem. Anyway, so yeah, so we're just gonna write out, and well, okay, so today we're gonna take like really easy cases. We're not going to like go into very details, not going to have generalized cases or something. Just gonna take like really easy cases. So yeah, I'm gonna suppose that n plus 1 can be written as well, I mean, it's gonna have a factor of 2, right? And then 2 times some prime q, some other prime. So the equation we get now is, so this is like the prime factorization of it. Anyway, so the equation we get now is p minus 1 is equal to, so phi of this would be, so n plus 1 times 1 minus 1 upon 2 times 1 minus 1 upon q. Okay, so let's just simplify this a bit. N plus 1, oh, I'm going to replace n with p already, why not? Because like, sorry, it's just going to be an extra variable if we don't, and we don't want that stuff to happen. So anyways, this is just going to be half, and this is going to be q minus 1 upon q. Now that's like taking common denominator and stuff. That's really elementary. I don't expect any one of you to not know that. It would be really weird if you did not know it. Anyways, so we're gonna move the 2 q's to this side, which means that it's going to be p square minus 1. Think about that for a minute, why that's the case. But it's really easy to see because anyways, yeah, that's going to be p plus 1 times q minus 1. So that's going to simplify as pq minus p plus q minus 1 is equal to p square minus 1. Now these two cancel out, so we get p square is equal to pq minus p plus q. Okay, that's pretty cool. That's like a simple, no, it's not really simple, but it's a Diophantine equation, right? Should be pretty elementary to solve. Again, I don't know, I haven't solved it yet. This is also improvised, which it shouldn't be, but anyways. Okay, so let's think about how we can factorize this. Okay, so the first thing to know is, let's see, so I'm going to factorize it a bit here, right? So p q minus 1 plus q, right? So okay, so if let's see, so if p is greater than, can p be greater than pq plus q? No, it can't, right? Yeah, it's impossible to. First, did I write here q prime? Yeah, I should have written it here before, but yeah, q is a prime number. Anyways, so yeah, so okay, so these are two primes, right? They're distinct primes. Okay, let's see how we can factorize this. So we can write this as q minus 1, and then we can subtract another one here, and we can write it as, okay, so we, oh no, we don't want that form, do we? Okay, yeah, maybe we should solve this quadratic in p. Let's see where that takes us. Right, so we're gonna get p squared minus p, let's see, so yeah, q minus 1 minus q is equal to 0. That's a quadratic in p, right? Let's develop some elementary conditions for p. So let's solve this using the quadratic formula, right? So this here will be our b. Our a is 1 because this is a monoquadratic, and this minus q, of course, yeah, this negative sign is also included. This minus q will be our c, right? Yeah. So anyways, the quadratic formula, I think I've like derived it or something once, but you can derive it using completing the square or something. Yeah. Anyways, it's really easy to derive it. Don't trouble yourself with that. Anyways, yeah, so we're gonna use it directly here, right? Because I'm assuming that you know what it is. Anyway, so p is equal to, right, so minus b, that's just gonna be q minus 1 plus or minus the square root of, okay, so that's q minus 1 whole square. I'm ignoring this minus sign because it's just gonna get cancelled out, and then it's minus 4 times a is 1 times c, which is minus q, so that's going to become a plus 4q upon 2a, which is just 2 here. So okay, that's the thing. Well, now we know that this thing is definitely greater than this one, right? Because we're adding a positive number inside the square root, so it's going to be greater. So we can remove this negative possibility because p must be positive. Anyways, yeah, I'm going to take this up here. Let's see, so so p is equal to q minus 1 plus square root of, we're going to simplify this, and you know the minus 2q's will cancel this one, so q, okay, that's going to be plus 2q plus 1 upon 2. Now I hope you can see that this is a complete square. It's going to be q minus 1 plus square root of, okay, so the square root of okay, so that's going to be q plus 1 whole square upon 2. This is equal to q minus 1 plus q plus 1 upon 2, and this is equal to, okay, so these cancel out, 2q, which is p must be equal to q, but we of course assume that p was not equal to q in the beginning, and of course this is a big contradiction if you think about it, because yeah, so these are two consecutive numbers and they have two prime factors in common, which is impossible. So what I proved is that p must be equal to 1, which makes it useless, makes it completely pointless, because, well, of course, p is a prime. So essentially what we've proved is this equation right here. Okay, so let me write down the conclusion of this work. Where do I write it? Yeah, I think it's like pretty good. Okay, what I proved is that there is no solutions such that n is a prime number and n+1 is 2 times another prime. Yeah, there are no solutions of this form. That's what I proved. Hey, this is actually pretty good. So this is like the first video, and I hope it would be a series. Anyways, yeah, this is like, I never thought. That's pretty good. Okay, nice.